Alrighty, so if y'all will look in the meeting chat, there are two links. Click on both those. One of them will lead you to a blank shader toy project, and the other to the completed project. So the new one should look like this, and the completed one should look something like this. But before we get started, I will explain a little bit what ray tracing is and why we kind of want to do it. So, first of all, the most standard conventional way of rendering things is triangle rasterization. I won't go too far in detail about it, but basically, you get a bunch of vertices, you map those to points on your screen, and you get a list of pixels, and then you do some sort of pixel processing, whether that's applying textures or lighting calculations. Benefits of that, super fast to render. It's less realistic though, but hardware supports it very well. It's a lot of modern GPUs are designed specifically to accelerate those calculations. Ray tracing, on the other hand, is much slower to render. Essentially, it's a simulation of light. It can approach photorealistic results, and there's much less hardware support, although it is gaining a lot more hardware support. Algorithmically, you have a conceptual camera point right there, and then you can imagine there's a 2D plane where you shoot a ray through each of the pixels and try and intersect some scene geometry. Once you intersect something, you can bounce around the scene and hopefully hit a light source. In real life, photons are released from a light source, they bounce around the room and they enter your retina. The problem with that is if there's a light way in the back of the classroom, you're going to have to do a lot of calculations. You're going to have to shoot a lot of rays, you're going to have to bounce around a lot, and it's an astronomical chance that they'll actually hit your photon. So an optimization programmers do is instead of shooting rays from all the light sources, they shoot rays from the camera and kind of work backwards. That way, a lot more rays are going to hit light sources. So what we're going to be talking about today is ray marching. It's a close cousin of ray tracing. A lot more people are familiar with ray tracing, and that's why I called it the ray tracing workshop. But it shares a lot of fundamentals with ray tracing. Primarily, since we're limited on time here, the benefits of ray marching is it's a lot less complicated to implement. As opposed to ray tracing, the intersection when you hit an object is calculated a bit differently. We'll see how that's done in a little bit. It's much quicker to create geometry with typical ray tracing. You need to create meshes made of triangles, and for our sake, that is a lot more complicated than we have time for in the hour. And there are also some extra cool properties I will show you later. An overview of the ray marching algorithm here. So if you're casting a single ray, you start at the camera point, and throughout all the scene, you look at what's the closest possible to you. Right here, you can see it's the ground down here, and so you move that distance in the direction the ray is pointing. So the ray starts here, pointing this way, says, hey, I can move that far, and it takes a step. Then at the next step, checks what's the closest thing you can hit again, which is this circle, and so takes that step forward. And it just keeps checking what it's closest to and taking steps. And that's why it's called marching. And then eventually, once the steps become small enough, you've essentially hit the object and you can detect a hit. Any questions on that part? And so implementation, what we're going to get is numbered pixels. So 0, 0, 0, 1, 0, 2, all the way up to the image resolution. And this is an image of what we're going to end up getting. And so now it's time to start programming. So, like I mentioned, go to shadertoy.com. You can start a new project by clicking that button. And you should be prompted with this cool color changing image. We are going to change that real quickly. And so what we're given, if you look at the top here, they give you a couple constants to play with. And essentially, this is a shader program written in GLSL. And so we are given a frag coordinate. That's the X and Y coordinate of a pixel. And this program is ran once for every pixel. So on your GPU, it basically says, hey, I got these many pixels. I'm going to run this program on every single pixel in parallel. And that's how it does things super duper fast. And so frag coordinate, or frag chord, that is the X and Y. And so what we're going to want to do is just output the color of the UV. Is that better? Or okay. Yep. And so if we change color to the UV and a 0, you'll see this nice pretty picture. The output is frag color, which we assign here, and takes the vec4, which is RGBA. You use vec4s and vec3s. You can also use those for X, Y, and Z, which is what we'll be using, but those also correspond to R, G, and B. And so right now, what this is doing here is mapping the screen coordinates from 0, 0 in the bottom to 1, 1 in the top. And the output color, you can see as it increases in X, the R increases, and as it increases in Y, the green increases. And so as both of those increase, you get yellow in the top there. And so now, I forgot to mention, if you don't feel like typing out all the code is in this other project. So if you just want to follow along and kind of understand how things work, you can do that. And so here, what we're going to try and do is shift it from 0 to 1, 1, all the way to having 0, 0 in the middle. So the way we do that is subtract half of I resolution x, y, and then once we do that, you can see the center is now dark and the edges are a little bit lighter. And then we are also going to want to change this eye resolution XY to eye resolution Y. And basically what that does is brightens up this edge. Since our screen is not perfectly square, we want this to map from 0 to 1 on the Y, and then we want to actually stretch out the X a little bit. So this goes from 0 to like 1.25 or somewhere in there. Or I should mention 0 to 0.5 and 0 to like a little bit past 0.5. So now that we have that, we can create a struct to store array. So struct array. This is how you define structs in GLSL. So we're going to want a float for color. We won't do any super fancy colors. I'll shorten that to COL. A vec3 for the position of the ray, and then a vec3 for the direction of the ray. And so now I'd like to, I won't do that. And now get rid of that comment since that's not accurate anymore. We can construct array. So array, say the name equals array. This is how you construct structs in GLSL. The color we'll just do as 1. The position we will do, we'll define it up here. So in GLSL, it's a lot like C, where you can define global constants like this. So define, we'll do camera underscore position, and we will make that a vec3. We'll go 0, 0. We'll go like, yeah, we'll go 0, and then -10. So that way we can kind of center our scene geometry around 0, 0, and our camera's starting back. And so here, all we need is camera position, and as long as you typed that define out correctly, that should be good there. And then we also need the direction, and so for that, we're gonna create new vector3, and we want the UV, the UV, and then we'll do 1, and then that will create a vector facing forward with a little bit of left, right, up and down changes based on the point in the camera it is. So this pixel will shoot forward, this one will shoot up, a little bit right, a little bit left and up, etc. And then we want to normalize this. And this basically makes it super easy to scale. If you're unfamiliar with vector math, it just means if you multiply it by some number, it will give you a vector of that length. And so we compile that, press this little play button to compile. The green border will signal everything's okay. If something's not okay, you'll get this little red box error. Sometimes it's a little hard to debug, so that one we were just missing that parenthesis. Now for the main functions, we are going to want a float get dist function, and this will take a point in the scene, so we'll just call that rpos for ray position. And this is gonna be the function that tells us what's the closest thing to the current point. And so for now, we'll do float d equals 0.0, and then return d. We'll replace that later. Right now we're just writing some skeleton code. And so now here we can do a vec3 ray march. This is going to be the meat and potatoes of our algorithm. And so for this one, if we want, we can return r.dir, and this is just a nice little debug thing. And so if we replace the color in the main image with ray march our ray, we should get a nice blue looking screen. And this shows the direction each ray is pointed. And so blue, if you remember on the axis, corresponds to Z. Red corresponds to X, and green corresponds to Y. So it's nice to do these sanity checks. And so on the right, it gets more pink, which means you're adding red. As you go up, it gets a little bit lighter, which means you're adding some green. So that's good. So now for ray marching, we're going to want a float dist. And to start, we are going to define a new constant. We're going to call this one infinity. And so you might notice it's a very large number, but it's not infinity. For our purposes, for all practical purposes, a really large number works as infinity. So now infinity, and so then we are going to create the loop that actually takes the steps. And so I also like to define a couple globals. So in GLSL, you can define global variables that can be used anywhere. And so what I like to do is in steps equals 0. That's all you have to do for those. And then for later, bounces. And then we're going to want to define a couple more constants. So max steps equals, we'll start at 50. Oh, don't need an equal sign there. So max steps 50. And then max bounces 2 is all we'll need for this workshop. And so now down in our loop, steps is already initialized, so you can skip that part. You want to check that steps is less than max steps. This basically just makes sure we aren't doing like thousands and thousands of steps in our scene and slowing down our performance. This basically is the bottle cap for that. And then we also, we need one more constant defined up here, and this is going to be the hit distance. And so we'll set that to a pretty small number, and so that means once we get this close to any surface, we're going to treat it as though we hit that surface. And so in our steps, we're going to want to take steps until the distance is less than hit dist. And then since it's a for loop, steps plus plus, and that is going to be what's looping for all these steps. And so all you need to put in the middle is dist is equal to get dist and pass in the ray position. And so that will go through the whole scene and return the distance to the closest object. And then we need to update the ray position. So ray position plus equals the ray direction times by however far we can move, so distance. And so that's essentially the whole hopping algorithm. And then outside of here, if we want to detect if we hit something, if dist is less than hit dist, we will return the vec3 of r dot color. You can also just return a vec3 of 1 right now, so RGB of 111. that will work too. But later we'll need to use that. And so now, if you, oh, there, I misnamed that. Everything compiles. So now we have to define the scene geometry. And so the way ray marching works is we need to define signed distance functions, which is basically just fancy lingo for saying how far am I from this object. If I'm outside, it's going to be some positive number to the surface. If I'm inside, it's going to be some negative distance to the surface. And so, first of all, they're all going to return a float. So the easiest one to do is a sphere. And that is going to take the ray position, the float radius of the sphere, and the position of the sphere itself. You can also copy this function if you're afraid of mistyping something. All the functions you should be able to copy from the other one. And so this one, well, how do we determine the distance you are from a sphere from any point? It's where you are to the center of the sphere minus the radius of the sphere. And so all we have to do is return the length. That's a built-in GLSL function that basically just says, hey, given a vector, how long is it? And so our position minus the position. Yes. Yep. And then minus radius. So that's the simplest way to write a signed distance function for a sphere. So now in our get distance function, we'll replace the default distance with actually we don't even need that. What we can do there is call the sphere, and so our position is given, so our pos, and then the radius of the sphere. For starters, we'll just do 1.1, and then the position of the sphere. And so we'll just do 0. We'll throw it up a little bit. So 0, 1, and then 0. So it's 1 up from the origin. And then now that we got that, if we hit compile, that should, I can keep it on that screen for a second. Yes, that should show up a color. Should show up a white circle. Maybe we just need that. Sphere r plus might have messed something up if dist is less than. Oh yes, good catch. So for loop, we want to keep going if the hit distance is greater than, well, if the distance is greater than the hit distance. So once it is close enough to hit something, then it will. And so now when we compile, you can see a nice white circle there. And so if we want to, I'll make the background black a little bit. And so all we have to do is change that to a vec3. So now we got our sphere. It looks like a circle, but trust me, it's a sphere. And so if we want to add shading, we're going to need to add normals. And so a normal, given a surface, is just the vector pointed straight up from it. So this desk, the normal would be pointed straight up. If you've taken physics, you know that the normal from the side of the desk is to the side. On a sphere, it's pointed away from the center. And so for ours, there's a nice little shortcut function. I won't go too in depth, but if you go to the completed example, there is a function called getNormal. Just copy that, and you'll want to paste it below the getDist function, since it uses that. Essentially, for those of you who are math nerds, it takes your point when you hit something, shoots out a little wiggle point in two different directions, and then based on those distances, you get two vectors, and you can take the cross product, which will give you the normal. And this is just the optimized way of doing that. I didn't come up with it. I got it from someone else, but that is essentially how that works. And so now, if we have the normal, we can go down here, and now we want to set the, actually, we'll want the vec3, call this normal equals get normal. We'll use this in a couple examples of how you can do things. And so just pass in the, that should be r dot position. And so now you do that, you get the normal, and then what we can do is, well, we want a light in the scene, so we need to make it nicer to replace, or like easier to replace, we can define a light position up here, and so that's going to be a vec3. You can make that whatever you want, but just for funsies, I'm going to show you how to make it spin around the scene. And so we're going to do 10 times and the sine of I time. This is one of the things they just kind of allow you to use in your shader. If you click that button, you can see all the things they let you use. I time is basically that little number down there. So if you hit play, that goes up, and so if we want the light to continuously spin and not just like fly away into oblivion, you need to have a sine function there. And so then the y, we'll just put it up in the sky a little bit, so at 5, and then we'll do 10 times by the cosine of I time. So now that will spin. Again, that constant is at the top here, so if you don't feel like typing it all out, it's right there. And now that we have the normal, we can change the ray color. So r dot color is equal to the dot product of the normal and the normalized, or I'll show you what it looks like with just the light position. And so the dot product basically takes two vectors, if you're unfamiliar. The more they're lined up, if they're directly parallel, they'll give you 1. If they're perpendicular, they'll give you 0. And if they're pointed in opposite directions, they'll give you -1. And so by taking the dot product, we can see how much light should be hitting that point. And so if we do that, you'll see a cool little super bright contrast there. That's because the light position is not normalized. We want that to be a direction. And so to fix that, normalize the light position. And doing that, you now get this super nice gradient. So if you go full screen, you can see the beauty of that nice little gradient there. And so now, what if we want to add new things to the scene? Here, you can use some Boolean functions. It's how I've heard of them referred to. Basically, the one we're going to be implementing right now is called the union operation, similar to the and. So if you have a Venn diagram, it's basically everything that's in both the circles. And so in order to do that, we need the float A distance to object 1 and float B. So those are going to be the two distances to two objects. And all we're going to do is return the minimum of the two. So float A, float B. That's all we need for that function. There's a couple other operators. I'll get to those in a little bit. But now, once we get to the get distance function, we can define another sphere. We'll just give it the exact same stats, except here we'll shift it a little bit over. So now 0, 0, 0. So like I said, identical to the first one, just shift it a little over on the X. And then to apply the union, all you need to do is, this should be a differently named variable right there. So then down here we can do D equals op union. The reason we're calling it op union is because union's keyword reserved in GLSL, so you can't use it to name functions. It'd be like naming a function float. And so op union, the first distance, the second distance, and now once we hit compile, you now see two spheres, and there's a lot of different Boolean expressions you can do. So if you go over to the completed one, there's a link I've included at the top that shows you a lot of the cool stuff you can do with ray marching. So if we go here, you can see the sign distance functions for a lot of objects. I've also included a couple of those here. So I got a box, an octahedron, and so if you want to copy those, you can. So Control C and go up to the sphere, put those right below there. And then I've also included a couple of Boolean operations. These are the cool things you can do with ray marching. And so if you copy the smooth Boolean as well as the rest of them all the way up to union, I can show you a little bit of why ray marching is a very unique and unreplaceable methodology. So if we go to get distance, instead of normal union, we can do the smooth union function. Oh, and that requires a smoothing parameter. So just add a little number at the end. Usually lower, you can see a bit more of the objects. So if you go 0.2, you can see the spheres have melted together, and I'll wait till it gets to a nice, yeah, right there. And so if we want to decrease the smooth union, you can start to see how they melt together. And so a couple other operators are subtraction. This basically takes shape 1 and cuts it out of shape 2. So you can kind of see it there. Another thing you can do is you go down to the completed solution. I'm kind of skipping over a little bit of the math here. Hopefully you can go in and look at it later if you want. But if you copy the mouse line right there and paste that right there, and then add a vec3 of mouse by -0 or multiply that by -5 and then toss in a 0 there. That's a quick way of making it so you have mouse controls as well. This is another one of the shader inputs they give you, iMouse right there. And so basically by clicking and dragging, it just feeds your program what pixel your mouse is hovering over. And by doing some math, we can make it so your camera moves around. And so from this direction, you can see the subtraction a lot better, where the first sphere just gets cut out of the second one. And so you can play around with those a little bit on your own time. There's an intersection, which basically says, hey, given these two objects, where are they both? And doesn't show anything else. XOR is the opposite of intersection. And then the smooth stuff basically just smooths it out a little bit. And so the other thing, if you want to include more shapes, go to the website I showed you, and you can kind of adapt those and just copy, paste them, and you'll have to change a few variables in order to make them working. But you should be able to copy what I've done with the sphere, the box, and the octahedron, and be able to get them working in your scene pretty quickly, pretty easily. And so now we would like some realistic shadows. And so if we go to the getDist function, we can add a new shape. So float d2 equals box. This is one of the shapes I copied. And essentially all it takes is your ray position, the dimensions of the box, and the position. So the box, we're going to want the R position. We'll give it dimensions 20 on the X. We'll make it a really, really narrow, or really, really short, and so it'll look like a big old plane on our screen. And so the position, I think I was playing around with this earlier. 0 on the X is -1 on the Y, and then a 0 on the Z. And then in order to get that to show up in our scene, D equals union of what's already in the scene and the new box. Got a syntax error, missed a parenthesis there. And then we call this one op union. Yep. And so now you can see a little bit of artifacting. Artifacting is an issue in a graphical program where you can see a problem with the rendering method. So here you can kind of see the plane curve downwards toward the object. And essentially what's happening there is we're taking a lot of steps really close to the object, but we're not actually hitting the object. And so by the time it's trying to hit the plane behind it, it's already taken too many steps. So in order to fix that, all you have to do is go back up here, replace that with 200. Oh, shouldn't do enter. And then compile. And now you can see the whole plane's rendering and there's no more the weird warping darkness around the sphere. And so now now we have a plane, and so on this plane we're going to want to see a shadow. And in order to do that, we're going to need to bounce the rays. So here we're going to create a new for loop for bounces. That's the variable we created earlier. Bounces is less than max bounces. And then we also don't want to keep trying to take steps if we've already hit the max steps. So max steps, and then bounces plus plus, and then within that we're gonna want to put double check something. Yes, we're gonna want to put all of this logic inside that for loop. So cut that, re-indent some of that so it's a little bit more legible. And so now that this gets repeated, we're going to need to break if it just doesn't hit anything in the scene. And so if we should define a new variable up here. So define no hit distance. So for our scene, it's all pretty close together. If a ray travels 1,000 units, it probably missed something. So for this case, we'll set it small, or relatively small, but if you get like a bigger scene, you're obviously going to have to increase that no hit distance. Yes.
To properly execute this, like when memory most of the time, what is ideal for vectoring? Like if you're a physics person, would you recommend that you start taking any DPT or calculus to get a better way around this, or like a vector specific type of math that would be ideal for this?
Most ray tracing is a lot of linear algebra, and so if you've taken a linear algebra course, you probably know most of the math. There's a lot of it, a lot of the advanced stuff is a lot of machine learning, a little bit, a lot of uh, there's for runtime programs, there's going to be a lot of noise. Right now, we're kind of uh, hand waving it away and with a single light source. But if you get multiple light sources and you get different colors, and you want like, if there's like a bright red object here, obviously some of the red light's going to kind of bleed onto the table. For that stuff, results are going to be very noisy, and advanced ray tracing topics are just.
When you say noisy, like you mean the actual noise, or like most or the code being just a lot of clutter?
I mean, the image itself will look staticky. So if I look at some, okay, none of these. I okay. Okay. Well, that just takes me there. Okay. Oh yes. So yeah, you can see on the left side, it's a lot of static. And basically what's happening is in most ray tracing scenes, once a ray hits a surface, you have to bounce it in a random direction. And so based on the material, if it's like 100% mirror, it'll bounce predictably. But if it's completely diffuse material, it could bounce in any random direction. And so you have to shoot a bunch of rays per pixel, and if they happen to hit a light, uh, it'll light up and look good. But the problem is a lot of them just bounce around and don't hit anything. And so you kind of have to figure out how to light those properly. It's a long and
And like with every bounce, the the photons are ever decreasing, right?
yes, yes.
And can you determine on how fast they can decrease or how slowly?
Uh,
Or is it just based on the calculations that you put, and it'll start with the lighting and it'll eventually on its own just like dissipate?
most of the time, most people, unless you're doing like fog or something like that, most times it will decrease by the color of what you hit. So um, that's a perfectly white light. If a photon hits that, hits the desk, it's going to make it brown. And then as it bounces around, it's going to lose more and more color. There's a lot of light theory to it. If you want to kind of figure out how that works, there's a lot of good YouTube videos on it. Um, it's uh, it's a complicated discussion, a little bit more than we have time for right now. Um, but coming back to this, so if we go to, yes. So we just defined the no hit distance, and so if distance is greater than no hit distance, we're just going to want to break out and not do anything. But essentially how we're going to do the simple shadows is once we hit a surface, since we only have one light, we're just going to point the ray directly at the light and ray march again towards it. And if it hits an object, so say the light's here, I'm trying to go through my laptop, if it hits that, we're just gonna output black. And so the way we do that, we're gonna have to uh, ray marching to the light, since it's not in our geometry, it's just gonna fly past it. And so if it doesn't hit something after it hits a surface, we can assume it made it to the light. So the way we're going to do that is add a bool, just call it hit equals false, and then if it passes the first no hit check, we'll just set it to true. And so now, then here we're going to have to do bounce adjustments. And so in order to hit something, we'll need, this is no longer going to be true, so delete that. So if you hit something and dist is greater than no hit dist. So now all we have to do right here is say, what do we do when we hit a surface? So if we hit a surface, we are going to want to point at the light source. And so how we do that is our dot direction is now the light position, that constant we defined earlier, minus the ray's current position, and then we're going to want to normalize that. Every time you do a direction, the vector should be normalized. So now that we got that, so now our ray is pointed towards the light, but the way it's positioned, it already triggered the no-hit condition. So if we just try and go through it again, it's going to be like, oh, well, I hit this surface. So we need to move it up a little bit. And so r dot position plus equals, I found 2 times normal times by hit distance. If you don't move it high enough, you can, or far enough away, you can see a little bit of artifacting, and that seems to be a good distance for that, I found, just by playing around with it a little bit. And so now position is updated, direction is updated, and then all we need to do is set distance equals infinity again. So now all the variables we've made are reset for the marching loop right there, and I believe if you hit compile, we now have shadows. And so if you let the light spin around, you can see the shadow spinning, and that yes, one last thing. If we set the ray color to just the dot product, there can be some more artifacts, and so if you just do the max there, that prevents it from the ray color from changing from negative to positive again if you get 2 negatives in a row from subsequent bounces. And that needs to be in floating point format. And yeah, that's essentially the workshop. If you want to play around, the easiest way of doing things is to just add and remove shapes from the get distance function. You can do some fun things. So like in this completed version, if you change this first union to a smooth subtraction, I believe you can get cool things like this shape, where it just kind of oscillates up and down. This
is like the shape like deleting and undeleting itself.
So in this scene, there's a sphere right here, and that's getting subtracted from a box. And the box is basically just oscillating up and down. So you can change the position of the box using the iTime variable I showed you earlier. And if you just use a sine function, it'll just keep bobbing up and down. Yes, so if I just change the smooth subtraction back to a union, you can see the sphere there and the box moving up and down. And so when you do the smooth subtraction, the sphere cuts away from the cube, and the smoothing function kind of makes it less rough. How would you have a second light source? Second light source, you would. So essentially, what you'd have to do when you hit the table is you'd have to shoot 2 rays. one going to each light source, and then take the I'd have to double check the math on if you like take the max of them. So if one of them hits it and the other doesn't, obviously it's not going to make the light from the first one darker. But then if you hit both of them, it's not gonna overflow to over one brightness. If that makes sense.
Wouldn't it be addition though? Wouldn't the two magnitudes of the light combined?
Yeah. Actually, I was probably overthinking that. Yeah, addition would probably be the solution for that. But yeah, in order to do that, all you'd have to do is, just send two rays. You might have to restructure the code a little bit to support that, but yeah. Any other questions? Yes.
And like for A games, how many rays are they shooting at typically when you're playing, I don't know, like something like Red Dead Redemption?
Red Dead probably doesn't use a lot of ray tracing. A lot of ray tracing benefits can be faked with triangles and making them a little bit translucent. A lot of AAA games, in order to get ray tracing like features, will not shoot every ray for every pixel in the scene. They'll just send sampler rays and assume pixels nearby are kind of similar.
That what screen space reflection is basically, because screen, I don't know if you've used it, right? That does support it. It tries to guess reflection and light balances based on only visible elements from your camera.
That is actually a triangle rasterization technique.
Okay.
And so that gets complicated, but that would be a fragment shader. Yeah, so that is a triangle rasterization technique. Basically, like I mentioned earlier, in the triangle pipeline, uh, once you get the pixels, you can also send data with the pixels. So like, oh, this pixel is at this point in the scene, and then you kind of look at the entire rendered scene on your screen and go, well, that's probably going to be pixels above here. If that makes sense. I don't know if I explained that very well, but yes, it is a triangle uh, technique.
And between the two, triangle rasterization is the most common and easier to use. And like,
Yes.
for example, if you're going for anything that's not realistic, basically almost anything Nintendo, you would use triangle. And then if you would make any from software, then you would be using ray tracing. I don't think any from software is actually. A lot of it's like Iron Man already does. A lot of games that. Yeah, I think that like 90% of games, like only in like the last maybe like 5 years, like ray tracing is starting to be a thing.
Ray tracing. All good. Ray tracing is really, really expensive if you want it to look really nice.
And usually you also need like actual graphics card that does support it anyway.
Graphics cards have gotten a lot better over the recent years, but they're still designed to crunch triangles and turn those into pixels, and so that is much, much faster. Yes.
How simple is making like a colored object in this?
Yeah. So we can actually make all the objects red really quick. If you just do comma 0 comma 0, they're all red now. Color would have added a bit of time to this meeting, so I didn't tackle it. But basically, what you would need is to figure out what object you're hitting. And so you'd probably want to create a buffer of objects. So just like an array of uh, objects, and maybe add a return to the getDist function. So maybe have it return index of the object you hit. So in this case, if you change it to a vec2, if you hit the, you'd also probably want to adjust the union function to also return which one you hit. And so if we go to op union, you'd want to do probably a vec2 just to pack that. And then you do if A is less than B, return vec2 A comma 0, just to have something to signal which option you chose. And then from there you can follow that down to get distance, returning not only the distance to the closest object, but the index, which will contain the color of the object as well. And then from there, the ray color, you can adjust that. You would, I believe.
Really good, thank you.
Yep. Thanks for coming.
Great night, guys.
You too. And then eventually, however you want to get the color, you just multiply the color by the shading light. So.
I always recommend to use floats rather than integers.
Floating point operations are a lot easier to use in this. You could set your there's ways to use integers, but floats when working with like any game engine stuff is a lot easier. The only caveat is you want to make sure you don't get too far away from the origin, because floating point numbers can only have they have like a band of accuracy. So if you're close to 0, they can get really really fine decimals. But if you're at like 10 trillion units away from the origin, the floating point numbers aren't going to be able to do the super fine numbers, because that region's going to have to shift to include the trillions or billions, however many far away decimal points you are.
They only have a certain number of significant.
Yes, that's the verbiage I was looking for.
There's like videos of Roblox worlds that demonstrate that, where it just teleports you X amount of units away from the world origin, and you can kind of slowly see the breakdown after the launch. Because it gets to a point where you'll see, like geometry, characters snapping to like a pretty like noticeable grid, like on the screen.
Mm-hmm. The easy way of avoiding that is to not actually move your character, keep your character at 0, and move the world around your character.
That's what Outer Wilds does, actually.
Oh, I was unaware of that, but that would make sense because you can fly long ways.
Yeah, and I think Kerbal Space Program also does that.
Outer Wilds, chunk out the time to play it, because you don't want to take breaks during it. Don't look anything up, just go into it blind.
One question I wanted to ask, would this system like this be able to support ambient occlusion? Or is that another triangle?
I'm okay.
So you know how like whenever like something like I don't know your hand is on a table, everything like under your hand kind of gets darker. Or like even in Minecraft, like if you look in the corners between
Oh,
also see it kind of gets a little bit darker. That's what ambient luminance is.
yeah.
Just like, oh, if there's a place that probably won't receive a lot of light, just don't make it look very bright.
Yep. And so that's where a lot of the computationally expensive stuff comes into play. Right now, once a ray of light bounces, we just point it directly at the light, and the dot product that we do right here, that is a good approximation of how much light will hit that. If you want to do actual calculations, you'll want to shoot random rays around.
Okay.
And so if you shoot random rays into that corner there, a lot less of them are going to bounce and hit a light than if you than like this table that's like right below the light. And so that's how you kind of get natural ambient occlusion. Um, Curious if no. Bingo. Uh, okay. Un momento. An image in new tab. So here is kind of like one of the staples of ray tracing. This is one of the most basic rooms that kind of shows off what it can do. And so you can see the ambient occlusion up there. I was hoping for a noisier version, but it's a little blurry, but you can see some noise down there. It's kind of staticky a little bit, and so um, that's kind of the battle you're facing there. I think if I yeah, I can leave that one. Give it a second. Give it a second. I have an example of fairly noisy. Uh, ignore the shader name. But here you can kind of see the noise from rays. And so in this one, I am sampling uh, a texture that they give you. Yeah, I'm sampling this texture, and so essentially what it is just RGBA noise, and uh, as you move through it, it kind of shifts between the colors. So it's not fully uh, staticky at every index, and so that's why you can see a lot of the softer shapes here. But if you shoot less rays per pixel, you can see a lot more dramatic of the noise. And so as you shoot more rays per pixel, so if we go to 5 again, you can see the probability. So right now the light source up here, the rays that hit here are pretty likely to bounce up and hit the light, and the ones down here are more likely to bounce off into the cube map. And I think if I remove that, now you can see the true lighting. Um, and so if we increase this to, well, this is probably gonna chug along. Oh, I don't even know if I can support that. Go. Oh, okay. That apparently I do need a cube map. We'll just choose a really dark one. So, what doesn't it like? Yeah, this one's pretty long. We'll just reload that and pretend we didn't do something that broke it. But then, Yeah, that's kind of the issue with some of these shaders. The more complicated they get, the longer they take to compile. And so here you can see uh, the issue with my noise sampling. Uh, okay, this might take a second, but yeah, as you can see, the noise is a lot smaller, less blotchy. So if you use white noise, which is basically the probability of good scientific